Swayam Prabha. Digital India. Educated India.
Hello everyone, today we are going to start week number 8. We started our discussion on finite element method in two-dimensional in the last week. In the last week we had seen different kinds of element that can be used to discretize two-dimensional domain, and then we had also seen how to write say functions for different kinds of element, and also how to do integration over each element numerically. Now, with this, we have all the tools more or less ready so that we can apply finite element problem in some two-dimensional problem, apply finite element method into some two-dimensional problem. Now, this exercise is divided into two parts. First part will take a problem which is scalar field. It means that our primary variable is a scalar, and that is the topic for this week. And the next week we will see when the primary variable is not scalar. For instance, if we have an elasticity problem, then how the finite element formulation needs to be done. Now, so we will, to start with, will not take a very specific problem, specific boundary value problem representing a specific physical phenomena. We take a general equation and then write the weak form of that equation. Then once that is ready, then while applying that weak form, we will take a specific cases and then see the application, and through that understand various steps involved in finite element method in two-dimensional problem. Okay, so first take a model problem. This is a problem with us, and then what we have to do is we have to find out the solution of solution uxy. U is a scalar field, is a scalar, the function of x and y. And so that this equation is satisfied in a domain. I have not given all these details on which domain it is to be satisfied, what are the conditions at the boundary. We will see that. So we have to find out the solution for a given A1, these A1, A2, A2, A0, F, these A0, these are the constants, and F and specific boundary conditions. Okay. Now, just to look at it, just to give a physical touch to this problem, to this equation. Now, for a specific case, if we take A11, A22 is equal to K and all these are 0, then it gives us a very well-known equation which is called Poisson's equation. And I and J are the unit vector in x and y directions. Now, there are varieties of physical phenomena that can be represented through Poisson's equation, and for instance, these are some examples where the physical process can be represented through the Poisson's equation. Now, this is the governing equation. Our essential boundary conditions will be on U or on the prescribed boundary, essential boundary, and then we also have a natural boundary conditions like this. Now, this is a general form of natural boundary conditions. Depending on what problem we have at hand, this expression will change. For instance, if it is a heat transfer problem, then our primary variable U becomes temperature T, then K, which is the constant, becomes conductivity, and then F, the source term, which becomes heat source, and these are the boundary condition for case of heat conduction case and then convection case. Similarly, if we have to for a problem like irrotational flow of an ideal fluid, our U becomes stream function this, and differentiation of stream function will give us velocity in various directions. These are our natural boundary conditions, and density will be the constant, and then mass production will be sigma. Similarly, torsion of a cylindrical member with constant cross section, same U will be stress function, and these will be the constant, material constant, and These are the source variable, and this is how these boundary conditions to be specified. So there are many physical process can be represented through this Poisson's equation, but to start with, we will not. It is just to put that equation in a proper perspective. But to start with, we will not take Poisson's equation. We'll write the variational statement of the entire problem, and then while implementing, we will take a specific case and then implement. And for that, we will take two cases. One is heat transfer problem number 1, and then we will also see torsion problem number 2. These two problems we will solve in this week. Okay, but other problems can, same philosophy, same steps can be implemented to other problems as well. Okay, so let us start with start deriving the weak form. So this is the equation. As we know, this equation is defined in omega. We know, we have seen in one-dimensional problem how to choose test and trial function. Similar concept will be applying here as well. So the next thing is we need to integrate the entire thing by parts, and then that will give us the bilinear form, this variational form. Okay. Now, since the expression is very big, so let us write in a very compact form. So that is F1 and that is F2, and with this our equation becomes this, right? Okay, so we will take now each term separately and then get the expression and then write the entire expression together. So these are the 4 terms we have now. Let's take the first term. So this term is this, and if we integrate it by parts, then you know that we will have an expression like this. Okay. Now, in this expression, this part can be further modified by applying the divergence theorem. And how it is done? Suppose this part is over the area, over the entire domain omega. Now, if we apply divergence theorem, then it will give us this integration over area will now integration on the boundary. So omega, this gamma is the boundary, and what is nx we will come shortly. So this is by applying the divergence theorem, and I'm sure all of you are familiar with divergence theorem. Now the same thing can be done for the second part. So if you integrate it by parts, we will have this, and then this part, if we apply divergence theorem, then this part will give us this. So this integration is now transferred on the boundary. Okay. Now, so now this is n. N is suppose if you are moving like this, the boundary of this domain. This is our omega, our gamma, and this is the interior of the boundary omega. So n gives you the outward normal. If you take any part, any small segment, suppose this segment which is ds, on that ds the n will give you the outward normal, and nx and ny are the component of this in x and y direction. Okay, so n can be written in terms of this. So this is part number, this first part, and the second part. Similar thing we can write for the these 3 and 4 is very straightforward. So this will give you the third and fourth part. Now if we put all the part together, then that will give us this is the entire expression. Okay, where f1 and f2 we have already seen. F1, f2 is this. What we'll do now is we will substitute f1, f2 in this expression and get the entire equation. So if you substitute that, so then we have this entire thing. Okay. Now, so next is this is, suppose this is Qn, and this, if you have already seen the similar thing in case of one-dimensional problem. This part essentially gives you the natural boundary conditions. We had seen that natural boundary condition comes as a part of our weak formulation, right? So this is the natural boundary condition. Now, next is so this is the weak form we have. Now next is, if you see, this will give us the bilinear form BWU, and this part will give us the linear term. And finally, the equation will be this. And the similar equation we had seen in case of one-dimensional problem as well, but in one-dimensional problem, expressions of this and this were different. Now, this is the expression we have for two-dimensional scalar field problem. Okay, so this is the weak form. Now, once we have this weak form has to be implemented, has to be applied or satisfied at every element, and when we satisfy this at every element, we will get system of n equations. N is the number of degrees of freedom for an element, and since in this case every node we have just one degree of freedom because it is a scalar field problem, so n will be the number of elements. So if we satisfy this on element, it will give us the algebraic equations at the element level, and once we have that, we need to combine this to get the global equations, and then solving and then post-processing, boundary conditions applying and then post-processing. Okay, so let's now apply this weak form on element. Just for the demonstration purpose, we take we'll take triangular element, but when we actually do some example problem, there we will take different kinds of element then apply. Okay, so suppose this is our domain omega, and this is the boundary we have. Now this entire domain is now discretized with some element. For instance, in this case, triangular elements. Now here I repeat one thing. We had already seen in the last class what are the different sources of error in finite element method, and one of the very initial source is domain representation. When we have a domain and that domain is represented through a collection of element, and in that representation we may have some error. For instance, if you look at these are the area which is not covered by the finite element discretization. Now this is an error we are making while representing the domain through a collection of element, and that domain, this error will go as we keep on increasing the number of element, means as we keep on reducing the size of the element, this error will go. Another way we can reduce this error by using higher order element so that the curvature can be captured. Okay. Now, so this is the finite element discretization. What we have to do, we have to take one element, and on that element we have to apply this bilinear form. So now this we have to apply this weak form. Now this weak form, if we write at the element level, represent at the element level representation will be like this. So it is on the element. Okay, and this gamma e is the element boundary. Now we will have a detailed discussion on this part, but it is of relevance to mention right now that you see, look at this element. The boundaries are essentially, these are the boundaries. Okay, so here boundary is essentially three lines. This is 1, this is 2, and this is 3. So gamma e essentially is this boundary plus this boundary plus this boundary. Okay, we will come to this term shortly. So this is the same weak form written, just we replace the entire boundary by the entire domain by the element domain, and now next is the choice of, we have to choose a test and trial function, right? We had already seen what are how to construct shape functions for different kinds of element, and that shape function will give us the test and trial function. So u can be represented by this, phi I are the shape functions and ui are the values at the nodal point. Okay, now and n is the number of nodes we have for the element. And now this can be replaced, this can be substituted in this equation. Phi can be chosen as w can be taken as phi. So the shape function, test and trial function, both are expressed in terms of this shape function. And if we do that, if we substitute w and u accordingly by the shape function at the element level, then what we have is, this is the equations we have. element level, and if we substitute this, del u del x will be the del u del x, u is represented by safe function, then derivative of u will be represented by the, we can compute by derivative of the safe function, right? So this is the derivative of safe function. This is how now we can write the entire equation in terms of safe function. Okay. Now please note the continuity requirement for this problem. We have this is the element, this is the term that we need to compute. So the minimum requirement is C naught continuity at the global level we discussed in the last class. In this problem also we need minimum continuity, which is C naught. Okay. Now, so this will give you some coefficient and then multiplied by the by u. If you put it in elasticity problem, this coefficient k, ij are the elements of stiffness matrix, and then this term will give this, and this is can be written as this. And again, if we put it in the form of in the context of elasticity problem, this will give the forcing term. Okay, so just as a special case, as I said, let us not bother about this special case right now. We will take this and apply finite element method for Poisson's problem. But just since we are discussing the element level equation for the general case, how it will look like for Poisson's equations is this. Okay, just use, if we substitute a00, a1 to a21 as 0 and a11, a22 as k. Now, so finally we have this equation, and then this equation can be represented like this, and then in the matrix form also this equation can be represented. This is a very familiar equation, you have already seen it. Now this equation is the elements, every matrix and vector now is defined over a two-dimensional domain, and this can be obtained by this. Now this entire thing need to be integrated over element domain, and we already know how to integrate this entire thing numerically over a triangle, over a quadrilateral. We have seen it. Okay. Okay. Now, so what is important just now, as I said, see, this integration is over this part, the first part, which is this BWU part. This is essentially, this needs to be integrated over the element domain. This is also integration over the element domain. We have already seen how to do that, but this integration is not in the element domain. This integration is defined on the element boundary. Now we will see how to deal with this boundary integration, boundary integral. Let's see that. So this is the boundary integral we need to perform for this element, for instance. Okay, and ds is, if we go along the boundary, the ds is any segment here. Okay. Now suppose these node numbers are 1, 2 and 3. Numbering order of node is very important. We had seen in case of I had mentioned that in previous classes as well. Again, I would like to re-emphasize this how you number the element, in which order the elements are, the nodes are numbered. That is very important. Okay. Now suppose we go like anti-clockwise direction, node number 1, then node number 2 and node number 3. Okay. Now these are, as I just now said, total element boundary is, now we have 3 parts. One is the boundary number 1, boundary number 2 and boundary number 3. And boundary number 1 is between node number 1 and 2, boundary number 2 is between node number 2, 3, and boundary number 3 is between node number 3 and 1. So we are now, so this equation, this integration can be written in terms of this. So this is performed over this boundary, this part is performed over this boundary, and this part is performed over this boundary. Now this arrow shows how the boundary is defined. Means boundary is defined gamma 1 is defined between node number 1 and 2. The starting point of the boundary is node number 1 and the end point is node number 2. So we are moving in this direction. This is important because we will see again when we write the shape function, this is the ordering is important, right? Now similarly, boundary number 2 between node number 2 and 3, this is how we are numbering it. Boundary number 3 is like this between node number 3 and 1. Okay, so this equation can be represented like this. Now what we have to do is, for a given q, we need to integrate that over this. For a given element and given q defined on the boundary of the element, we need to evaluate this on this boundary. Okay, now let's so these can be written as this. Why? What is this term? This term is qi is the q at the ith node of the element, and qi1 means it is the contribution at the ith node by boundary 1. Means qi1 is the, if i is equal to 1, then this becomes, for q1e, this becomes q11 plus q12 plus q13. So this means the contribution at node number 1 by boundary 1. So contribution at node number 1 by this boundary, and this gives you contribution at node number 1 by boundary 2. So this is contribution at node number 1 by this boundary, and this gives you contribution at node number 1 by this boundary. Okay, now just by looking at it, we can say, we will also see when we write the shape functions, but just looking at it by intuition, we can say that contribution at the node number 1 we will get from this boundary and from this boundary. From this boundary, there will be no contribution at node number 1 for this integration. Okay, now so this will be clear if you look at the shape functions. Okay, now we need to again take say node number 1, and this is how, suppose we are defining the node 1, 2 and then finally 3. These are the shape functions we have seen in the previous week. So in order to find out q1, suppose I want to find out q1 requires integration gamma 1. Gamma 1 means in boundary number 1, and that requires phi 1e, then qn and then ds, plus then integration gamma 2, then phi 1e qn ds, and then plus integration gamma 3, then phi 1 qn and ds. Now look at, so this is for this element, this is for first boundary, second boundary, third boundary. Now look at the shape functions now. Now at element number 1, when we integrate over node number 1, 2, this is how the shape function varies, right? How the shape function varies. And if we take, so this is how the shape function varies, this is this part. Now if we take again node number 1 and contribution from this boundary, this is how the shape function varies. How shape function varies. But if we take this term means this boundary 2, 3, you will see that phi 1 is 0 along the entire boundary. So phi 1 will be 0 along the entire boundary. So this contribution automatically becomes 0. And similar thing we can check for if we take boundary number 2, node number 2, you will see that node number 2 we have contribution from this boundary and then contribution from this boundary. On this boundary, phi 2 will be 0. Entire boundary phi 2 will be 0. So we will contribution at node number 2, this and this will contribute. Similarly, at node number 3, only this boundary and this boundary will contribute. At this boundary, phi 3 is equal to 0. Okay. Now next, so this we understand when we integrate over the entire boundary and write this expression as the integration, summation of integration over individual boundary, it is not all the boundary will contribute to a particular node. It all depends on how this F function varies within the element. Okay. Now, take some, this is a discretization, take some, suppose this is our specified Q1, at the essential boundary, these are the values specified, right? First, take some intermediate elements. For instance, these 4 elements, just to make the point, this can be shown for any element, any intermediate element. Suppose these element numbers are 1, 2, 3, 4 like this, and these are all our elements. Okay. Now, so you see, for this element, suppose this is Q1 defined, this is Q1 defined here, and for this element this is Qn defined here, Qn defined here. Okay, this is for element number 4, this is for element number 2. Okay, for this boundary, Now the body has to be in equilibrium. If the body is in equilibrium, every point has to be in equilibrium, right? So in this boundary has to be in equilibrium. The equilibrium condition says if you do not have anything prescribed on this boundary, we have Qn specified on these boundaries. Okay, but if we take these particular elements, element number 1, 2, 3, 4, on this element there is no boundary where this condition is specified. So all boundaries are the internal boundary, right? In this case, so these two forces will cancel each other because equilibrium has to be maintained, right? Similarly, these will cancel each other, these will cancel each other. Equilibrium has to be maintained. Similarly, if element number 1 is connected with another element, which is again the interface is internal, there is no Qn specified there, then this will also vanish, this will also cancel each other, these are all cancel each other. So from this logic we can see that this boundary integral, there is no point in evaluating the boundary integral on a boundary which does not coincide with on the boundary of an element which does not coincide with the boundary where Qn is specified, right? For instance, in this element, none of the element boundary coincide with the boundary of the domain where Qn is specified, and therefore we will see that all these are internal, so it will cancel each other. Therefore, there is no point in evaluating this boundary integral part for these elements. We have to evaluate the integral part only for those elements and only for those boundaries where element boundaries where those boundaries coincide with the boundary of the domain where Qn is specified. For instance, if we take these 3 elements 5, 6, 7, these are the boundary elements, right? Now, if you take element number 5, first take element number 6. Element number 6, this boundary, on this boundary and this boundary, this is an internal boundary. So these two will maintain an equilibrium. So these two will also maintain an equilibrium. Okay. Similarly, these boundary will also maintain equilibrium with some other element. These also will maintain equilibrium with some other element. But these also will maintain equilibrium with some other element. But look at element number 5. On this boundary 3, 2, and for element number 7, again boundary these 1, 2, 3 are not the global node number, these are the element level node number. On this boundary we have this specified Qn. So boundary integral needs to be performed on this boundary. Okay, and this will contribute to node number 3 and node number 2. This will also contribute to these 2 nodes. This will not contribute to this, but on these 2. Okay, things will be clear when we take up an example and see how these boundary integrals can be evaluated. Okay, now, so now the question is how it is to be integrated now on this boundary where the conditions are specified. Now, I would like to take you to the discussion on 1D element. If you remember, in a 1D element, if you have a distributed forces along the length of the element, and this is how we had seen f can be calculated, where x1 and x2 are the coordinate of node number 1 and node number 2. Phi I is the safe function defined on this element, and fx is this, this is fx bar, and this is also x bar. So fx bar is the local coordinate system. We will apply the similar concept here. Now, so this is our next, this problem, right? On this boundary you have to do this integration. Okay, now this is the integration we have to do. Now define a local coordinate system like S. Okay, it is very similar to x bar that we have defined on this boundary. Okay, now so, and suppose on this this is written as Qn as a function of S. S is the boundary. But what would be the direction of this boundary? S cannot be defined in this direction. S cannot be defined in this direction. The reason is, as I just now said, how you order the numbering, that is important. According to our calculation, our derivation, numbers are like this. This is the order we have defined: 1 2 2 3 and then 3 1. So 2 3 means this direction, a local coordinate S is defined. Okay, now as I said, these are the local coordinate S is defined. Now on the all boundary, there are 3 boundaries. All boundaries, let us define this S. This is S, this is S, and this is S. This S starts from here 1, and then between 1 and 2, this 1, and between 2 and 3, between 3 and 1. Okay. Now, so what next is, this is done, right? Now let us see how this to be performed. Okay. Now suppose I want to evaluate, say I want to evaluate integral on this boundary 1 and 2. So we define a local coordinate, say S. Okay, and for this local coordinate, for this S, our starting point is node number 1 and end point is node number 1. So on this boundary, you look at what will be your safe function. Your safe function is this, and this is not the additional safe function we want to put in. If we evaluate phi 1, this phi 1 on this boundary, we will get this, which is shown by red color. Similarly, this is for phi 1, right? Now, but this is phi 1 on boundary 1 2, right? Similarly, if we this is S and starting point is 1 and end point is 2, on this boundary if you evaluate f2, this evaluation will be this. So this will be f2 and defined over 1 2 boundary, right? And then on this boundary, this is our S, and what is the f3? You will say f3 is 0 on this boundary. So sorry, not f3, phi 3 is 0 on the boundary. So phi 3, which is defined on boundary 1 2, that will be 0. Okay, so this is how the safe functions are now written on this individual boundary. Now what we do is we will take an example problem and then see how this boundary integral, with this understanding, we will take an example problem and then see how this boundary integral to be performed for a given element. Okay, now so take one first take one element. Okay, take a triangular element. Just for demonstration purpose, as I mentioned, we had taken triangular element, but the similar exercise can be shown for any other element. Suppose this is the element, and then we have this is the node, this is the node, this is the node, and suppose the node numbers are 1, this is 2, and this is 3. Anti-clock direction we have given the node number. Okay. Now, suppose here we have some Qn specified on this boundary. So this is a boundary, this is the element located at the boundary of the domain, and on this element boundary, boundary 2, 3, these conditions are specified. So suppose this condition is your, take any condition as say Qn, which is function of s, that is equal to Q0, a constant value to start with. Okay, so this is a constant value. What is the job now? Job is because of this, because of this Qn, we need to find this element is say this element is E. This element is E. So our job is to find out what is QE. QE will be Q1, Q2. This will be Q1E, Q2E, and Q3E. We need to find out. This. Let's do that. Okay. So we define a coordinate like this. This is our coordinate. Say, define a coordinate S. First, let's say this coordinate. Okay. Now, so what we can write is safe function. Safe function we can write as this. Okay. Now phi. So what will be the safe function? We have just now seen on this. Safe function will be this, and this safe function if we write, then phi